Hello? Uh, can you guys hear me? Okay, I think we're gonna start. Okay, so my name is Aryan.
My name is Samyak, and we're second year students. Okay, so here's the outline of what we're going to be going over. So some things you should note is that the questions that we're going to present you are from our own past midterm and past final exam questions, uh, questions we found challenging or thought were a good idea to do. And another thing you should note is that for related rates, this was a topic never covered before. So I did a practice question for it at the end alongside a website that you guys might find helpful. It has questions similar to what was performed by Natalia, but just note that the format might be different because we never covered it.
Okay. Also note that all the topics that we cover, like we did not cover all the topics for the exam, such as MVT and IVT.
The reason for this is because most of the topics involving this were straightforward proofs. So we thought you guys already have all the resources for that. It was more important to focus on these topics. So
Okay, so we're gonna start. So for equation, so we're gonna create an equation sheet. We always tend to forget our sign, like what sine of an angle is, or like what tan of an angle is, and so I've created a chart for you guys to remember. So, and it's really easy to remember as well. So sine, cos. So you would write sine, cos, and tan on the columns. Then for the rows, you would write 0, pi over 6, pi over 4, pi over 3, pi over 2. So the only thing that you have to remember is the first row for sine, which goes 0, 1 over 2, 1 over root 2, root 3 over 2, and 1. Now, once you have the row for sine, all you have to do for cos is flip it. So you go 1, then 0, root 3 over 2, 1 over 2, and the middle stays consistent. And for tan, you divide sine over cos. 0 divided by 1 is 0. This would be 1 over root 3, 1, root 3, and 1 divided by 0 is infinity. Now let's go to trig derivatives. So sine of the derivative of sine is cos of derivative of cos of theta is negative sine theta. If y was tan x, derivative of y prime would be secant squared x. If y equals cosecant x, y prime is negative CFC x, y equals secant x, y prime equals secant x tan x. And if y equals cot x, y prime would be negative cosecant squared x. So these are your derivatives for your basic trig functions, and I would highly recommend you to copy this down and create your own equation sheets, as these will become handy for questions that we will see later on. Now for derivatives of inverse trig functions. So y equals arc sine of x prime would be 1 over root of 1 subtract x squared. Y arc cos. Also note that there isn't a way to memorize all of these. I would like, there isn't a pattern either. So you would just have to like memorize everything. Y prime equals 1 over 1 y, y equals arc tan of x, y prime would be 1 over 1 plus x squared. If out of all these functions you were to memorize one of them, I would highly recommend arc tan of x, because you'll see this everywhere. Now for arc cosecant x, y prime equals 1 over the root of x, square root of x squared, subtract 1, y equals arc secant of x, y prime would be 1 over root x, x squared, plus 1, y is equal to arc of x, y prime would be negative 1 over 1 plus x squared. You would see here that there is a pattern for arc tan of x and arc cot of x, and the difference is the negative sign. So that could be really helpful for you to remember. And have you guys touched on hyperbolic functions? Yes, okay. So I will go over them really quickly. So hyperbolic sine is e to the x subtract e to the negative x over 2. X equals e to the x plus e to the negative x over 2. You can see the difference is the positive and negative sign. And similar to the normal trig derivatives, they're very similar. So y equals y prime equals, but there is a difference where the derivative of cos of x does not equal negative sign of when you're talking about hyperbolic. So y equals cos of x. If you do y prime, that just equals hyperbolic sine. Equals secant squared x hyperbolic cosine negative cs x cot. There should be an h there. Negative c h x tan of x. And finally, we have hyperbolic cot, which equals negative. Oh, whoops. CSE and an H. So you can see that if you memorized this, the only difference is that these three have negative, and instead of the normal trig derivative, the normal function like cosecant and cot, you just have hyperbolic cosecant and cot.
Okay, now we'll move on to some trigonometric questions. These are questions that we found on our midterm, and they were very similar to the ones we found on our final exam. So these are some good questions to note. So a good approach to these type of questions will be to first notice that let a variable equal, so we'll let theta equal cosecant inverse 1 over x. Remember, cosecant inverse is just our cosecant. So now you can move cosecant to the other side. So you get cosecant theta equals 1 over x. But recall that cosecant is just 1 over sine. So this simplifies to sine theta equals x over 1. Okay, now let's draw a triangle to represent this. Remember that sine theta is, if you remember the common rule, SOHCAHTOA. So in our triangle, if this was theta, sine is opposite over hypotenuse. So this will be x, and our hypotenuse is 1. Let's calculate this side first. Let's just calculate the missing side. By Pythagorean theorem, you know this is 1 squared equals x squared plus, let's call this b, plus b squared. Let's solve for b. You get b squared equals 1 squared minus x squared. And you get b equals square root 1 squared minus x squared. So that's your b value right there. Once you solve that, now recall that we want cot of y. So we want cot, one sec. Okay, we want cot of cosecant inverse 1 over x. This is just theta, so that's the same as cot theta. Let's look at our theta. Remember that cot is cos over sine. If you forget this, just remember your ratios that tan equals sine over cos, and then if cot, then cot is 1 over tan. So you get you get this relation. Okay, so now let's compute cos over sine. Cos, remember that cos theta is adjacent over hypotenuse by our a triangle. So you would get adjacent, which is I'm on eraser. 1 squared minus x squared over 1, because our hypotenuse is 1. And our sine theta is, recall we calculated that right over here, is x. So cot theta simplifies to, it's just cos over sine, so you get 1 squared minus x squared divided by x as your final answer. This is a good trick to do for these type of questions when you have an inverse inside. But let's say you didn't have an inverse in the inside, you had it on the outside. So now, first of all, notice that 8 pi over 3 is greater than 2 pi. That means on our unit square, it makes a full rotation from the beginning and comes back around. Yeah, so now if we take 8 pi over 3 minus 2 pi, you get 2 pi over 3. This lies in the second quadrant. So this is 2 pi over 3. But we need our relative angle over here. So since this is pi, we can compute alpha equals pi minus 2 pi over 3 equals pi over 3. Now you get cos pi over 3. This is your inside angle now. Erase that. And recall from the one my partner did, you get cos pi over 3 is 1 over 2. So we know you should have these memorized. It's a good idea to, or make a table on the exam. So you get that's equal to 1 over 2. But remember, it's in quadrant 2. So you know that it has to be negative by cast. Okay, so now we have sine, let me write in black. Sine inverse cos 8 pi over 3 simplifies to sine negative 1 over 2, which is equal to, you can also, again, look over here. You see that sine 1 over 2 is pi over 6. So sine negative 1 over 2 is negative pi over 6. So you get that equals pi over 6. And that's your final answer. Okay.
Okay, so moving on to the algebraic definition of limits, some of the questions that you will encounter on your exams will ask you to classify the type of limits that you get, and it's very important to know the different types. So for limit, if the value f of x approaches L as x approaches C, then we can say that L is the limit of f of x as x approaches C. So this is equivalent of writing limit of f of x as x approaches C, which is equal to L. Now, if you were to write this as a delta epsilon, you would write for all epsilon greater than 0, there exists a delta that is also greater than 0, such that if in, oh, whoops, that should be a C, less than epsilon, implies f of x subtract L is less than epsilon. For limit at infinity, if the values of f of x approaches L as x grows without bound, then L is the limit of f of x as x approaches infinity, but I'll just not write that. So limit of f of x for infinity equals L. So here, instead of writing delta, you'd write n instead. And this is a very easy way to classify if you need to write n or epsilon. So for all, I meant delta, sorry. There exists an n greater than 0 such that if x is greater than n, implies that f of x subtract L is less than epsilon. For similar to the last two, you'd word it the exact same way as these two, and to prevent, to save time, I will just skip the steps and just write that. So this would be limit of f of x as x approaches C equals infinity. So notice here that you have infinity. So here, instead of epsilon, you would write m. So for all m greater than 0, there exists an epsilon greater than 0 such that if in the equality implies that f of x is greater than m. And for the last, you would have limit, for infinite limit at infinity, limit of f of x as x approaches infinity would equal infinity. And if you notice again, instead of epsilon and delta, you would have to replace them with n and m. So for all m greater than 0, there exists an n greater than 0, such that if x is greater than n, implies that f of x is greater than m. So I would highly recommend you all to know how to do this, as this is very important for delta epsilon proofs. So let's go to a very simple example. This should be an equals 1. So this type of example, it is the limit at infinity. At infinity. And as we see here, we have, instead of delta, we have n. Oh, n, sorry. So in order to start the proof, you always want to write your claim. So you want to claim that for all epsilon greater than 0, there exists an n greater than 0, such that if x is greater than n, implies that x plus 1 over x subtract 1 is less than epsilon. Now, what you want to find is a relationship between n and epsilon. And in order to do that, let's start with our scratch work. So you would start with this side. So x plus 1 over x subtract 1 is equivalent to x plus 1 subtract x over x, which is equal to 1 over x. And you know that that is less than epsilon. And since we have the absolute here, we can split it where you don't use an absolute. So this is equivalent to negative epsilon less than 1 over x less than epsilon. Now you want to find what we're given is this. So you want there to be an x, not 1 over an x. So let's flip everything. So this would be negative 1 over epsilon. And since you're flipping the signs, note that you also have to flip the greater than or equal to sign. So this would be x, 1 over epsilon. Then you can see that you're given x is greater than n. So you want to look at this part of the equality. So this implies that n must be 1 over epsilon. And notice that all of this was your scratch work. So now you can actually start the proof. So for proof, you always want to start off with whatever you were given. And so since we found that n should be 1 over epsilon, choose n to be 1 over epsilon. Then for all epsilon greater than 0 and greater than 0, we have x plus 1 over x subtract 1. I'll just skip all the steps. You do not need to rewrite the steps because you showed it in your scratch work. We know that this is also equivalent to 1 over n, since if you look at the green highlighted x equals n, and you know that n equals 1 over epsilon, which is exactly epsilon, which is what you wanted. Always make sure to write the box or QED, as you do not want to lose silly marks.
Okay, now moving on to 1 over x squared. We're going to prove that's continuous on 0 to infinity. You might have done a similar question in class that was 1 over x. This one's a very similar question, but it requires a little more bounding. Okay, let's start, like my partner said, let's start off with the claim. So for all epsilon greater than 0, there exists delta greater than 0 such that x minus c is less than delta implies 1 over x squared minus 1 over c squared is less than epsilon. Okay, let's go on to the scratch work. Okay, let's start with our inequality, 1 over x squared minus 1 over c squared. We can get a common denominator by multiplying this by c squared and multiplying this by x squared. That gives you c squared minus x squared over x squared c squared. Now, notice by absolute value properties, you can factor out a negative and it'll go out of the absolute as a positive. So we can flip these two around. It's perfectly valid with absolute value properties. So this will give you x squared minus c squared over x squared c squared, which is equal to x minus c, x plus c, from our formula a squared minus b squared equals a plus b, a minus b. So now divide that by x squared c squared. Now we can, this is equivalent of writing x minus c, because since they're multiplying terms, this will all even out in the end anyway, times absolute value 1 over x squared 1 over c squared. Okay, the first thing we need to do is notice is that we have x minus c is less than delta. So we know this is less than delta. We want to find a bound for these two because they contain x and we need a way to bound them. So let's start with x plus c. So let's bound absolute value x plus c. Okay, so let's let delta be less than equal to 1. That'll be our bound. So we have x minus c is less than equal to delta. So then x minus c is less than equal to 1 because delta is less than equal to 1. Then we get minus 1 less than x minus c less than 1. You can break the absolute value property like that. Move the c over, you get c minus 1 less than x less than c plus 1. We want to compute the max of this because it's a bounding, right? So we, yeah, okay, we calculate the max of c minus 1 and c plus 1. Notice that for some values, c minus 1 is greater if c is negative, and if c is, and for some values, c plus 1 is greater. So the perfect way to get a perfect bound for this would be to take absolute value c plus 1. So we can choose the bound as absolute value c plus 1. Let's just highlight this so we remember. This is our bounding for x plus c. But now we still need to bound 1 over x squared. So now we can choose another bound for delta to be less than equal to c over 2. This is just a common bound that's chosen to avoid overlap of the thing. So we get minus c over 2 is less than x minus c less than c over 2 by the same idea as over here. You move the c over, you get c c minus c over 2 less than x less than c over 2 plus c. Forget this. Okay, that gives you c over 2 less than x less than 3c over 2. Okay, but we want to bound for 1 over x squared. So let's take the reciprocal. Remember that when you take a reciprocal, you have to flip the sides of the inequality. So you would get 2 over c greater than x, x over 1. Let me fix that. 1 over x, 2 over 3c. Let's square it because we want 1 over x squared. Gives us 4 over c squared greater than 1 over x squared greater than 4 over 9c squared. That's just taking the square. So let's just write that. Square all. Okay. Now, clearly you can see here that the max of the max value here is, let me write that down. Max is 4 over c squared. So that's our second bound. That will be our bound for x plus c. So we know this is less than delta times our bound for x plus c, which was absolute value c plus, it's x plus c. So absolute value c plus 1 plus c times our bound for 1 over x squared, which is absolute value 4 over c squared times 1 over c squared, which is equal to delta times 2 absolute value c plus 1 times 4 over c to the power of 4. And we can choose our value. So this is equal to epsilon. Let's solve for delta. You get delta equals epsilon times c to the power of 4 over 4 times 2 absolute value c plus 1. So this is our choice of delta. Now, when we're writing our proof, okay, so first of all, make sure that when you're writing your delta, let it be the minimum of all the bounds you chose. So one of our bounds was 1. The second bound we chose was c over 2. And the third one we chose was our delta choice, in case delta is less than both of them. So 4 times 2 absolute value c plus 1. Then for epsilon greater than 0 and absolute value x minus c less than delta, we have 1 over x squared minus 1 over c squared equals the same way we did it before, x plus c which is less than delta times 4 times 2 alpha c plus 1 over c to the power 4. This is just the simplified form, just to make life easier. Which now, if we plug in our delta value, which is equal to epsilon times c to the power 4 over 4 times 2 alpha c plus 1, you'd see that everything cancels out nicely. And you're left with epsilon as wanted. Off page.
Also note that that question was on our midterm for fall 2019. So I would highly recommend you to look that over again. Also, the next question is a very fun proof. Is with arbitrary values. So we're given limit of f of x as x approaches c equals a, and limit of g of x as x approaches c equals b. And you want to prove that limit of f of x plus 2g of x as x approaches c equals 2b plus a. So in order to do these types of questions, if you are confused, you always want to write the givens. So so let's start with scratch word. So we're given limit of x approaches c of f of x equals a. So we could write this as for all epsilon 1 greater than 0, there exists delta 1 greater than 0 such that one implies f of x subtract a less than epsilon 1. You also know that limit of x approaches c of g of x equals b. Therefore, for all epsilon 2 greater than 0, there exists delta 2 greater than 0 such that x minus c less than delta 1 implies g of x subtract b is less than epsilon 2. Now, what do you want to show? You want to show or prove that statement, and which you could write in delta epsilon. So for all epsilon greater than 0, there exists delta greater than 0 such that if x minus c in between delta implies f of x plus 2 of g of x subtract 2b plus a is less than epsilon. And this is by definition. Now, if you consider this side, and let's say that's star, you can simplify this to something that you already know. So star is equivalent to f of x plus 2g of x, subtract 2b, subtract a, which is less than epsilon. Now you can rearrange this equation. So that is equal to f of x, subtract a, plus, you can factor out the 2, g of x, subtract b. And you also know this is less than epsilon, but you do not need that right now. Now you can split the absolute, so that is also equal to, so instead of, when you do split the absolute, it would be less than or equal to f of x subtract a plus 2 g of x subtract b. And look what we have right here. So we have two terms that we already know. So here we know that these two and these two. So what can we say about that? We can write that this is equal to epsilon 1 plus 2 epsilon 2. Now we want this to be less than epsilon. So what values of epsilon 1 and epsilon 2 do we choose? So there are many different values. You can choose any values that you want. For example, I will be choosing epsilon 1 equals epsilon over 2, and therefore epsilon 2 must be epsilon over 4. If you're confused on how I got epsilon 2, let's on the side, I will do epsilon 1 plus 2 epsilon 2 equals epsilon. So we chosen epsilon 1 to be epsilon over 2 equals epsilon. So we're just subbing in epsilon. Now, if we isolate for epsilon 2, epsilon subtract epsilon over 2, then you simplify that, you get epsilon over 4. And that's how we got the values for epsilon 1 and 2.
I have a question.
And now, since we have the two values for epsilon 1 and epsilon 2, we can go ahead onto our proof. So proof, for all epsilon, the standards, for all epsilon greater than 0, and subtract c less than delta, let us choose epsilon 1 to be epsilon over 2, epsilon 2 to be epsilon over 4, and let delta be minimum of delta 1, delta 2. This is because when we substituted for delta 1 and delta 2, we had to, there had to exist, oh, that's wrong. There had to exist a delta 1 and delta 2. So that's why we have to write that delta has to be the minimum of delta 1 and delta 2, else I would think you'd lose marks. Then we can write f of x plus 2g of x subtract 2b plus a less than or equal to f of x. These are the same steps. And we know that is less than, oh, I made a mistake there. This should be less than, because when you are subbing in f of x minus a, there's a less than. So this would be epsilon 1 plus 2 epsilon 2, which we know the values of epsilon 1 and epsilon 2, which is epsilon over 2 plus 2 epsilon over 4 equals epsilon as wanted.
Okay, now let's move on to infimum and supremum. All right, so this first one is a question that tricked a lot of people in our examination, so I think it's a good question to go over. So x is such that x sine of x is greater than or equal to -1. So let's recall the graph of a sine function. So we have, it looks, oh, oops. It looks something like that. Yeah, okay, it looks something like that. The point is, the minimum value is -1, and it occurs an infinite number of times as sine goes on. So there is no, so recall that here x refers to the angle. So there's an infinite number of angles such that this is a minimum value. Therefore, you can't determine these. Both of them are undefined. There's no one single value for them. Now let's move on to 1 plus 1 over n. Okay, so notice that n is an element of natural numbers. And what is the smallest? Okay, and you have 1 over n. 1 over n is at its greatest value when n is at its smallest, because you want to minimize the denominator, right? And what is the smallest possible natural number? 1. So our smallest value is 1 plus 1 over 1. So 1 plus 1, 2. So the supremum is 2. The infimum, on the other hand, is, okay, notice that 1 over n, what happens as n grows larger? Infimum is the smallest possible value. So as the limit of, if we take the limit of this, as n goes to infinity, you notice that this approaches 0. Even though it never actually equals 0, since it approaches it and goes towards it, it's still the infimum. Now, absolute value x minus 1 less than 2. This is a pretty simple example. You just recall your absolute value properties. You just solve for x, which gives you minus 1 less than x less than 3. So you can put your values right there. There's a typo on this one. The 2 should be in n. Now let's calculate. Notice that, this looks a little tricky at first because you have both the numerator increasing and the denominator. So how can we approach something like this? Infimum for the second one. Oh yeah, sorry, 1. Sorry, yeah, 1 over n is 0. So 1 plus 1 over n, 1 plus 0, yeah, 1, my bad. So thank you for that. So yeah, back to this. So if we have n over e to the power of n, this might look a little tricky because both the numerator and denominator are increasing. But notice that the denominator grows at a faster rate. It grows at an exponential rate. So this grows a lot faster than this grows. So one way we can think of this is basically we know that this value will be a lot larger at a faster rate than this value. The n is seen as like in terms of a constant in terms of it. So by this, we know that the infimum for this will be 0 because e to the n will be approaching infinity approaching a lot faster than n approaches infinity. The supremum for this is when n is at its smallest value again. So that's pretty simple to calculate. It's just 1 over e. The same logic where if you consider the smallest possible number, so 1 over e to the power 1. So that's just 1 over e. So that's a pretty simple example.
Okay, so let's move on to Hospital's rule. I will state the general definition. If the limit of x approaches a of f of x over g of x has an indeterminate form. Which is any of these forms: 0 times infinity, infinity times 0, 0 times 0, 1 over infinity, infinity over 0, infinity minus infinity. So if it has any of these forms, you could calculate that limit by taking the derivative of f of x and g of x. X to a, so this would be f prime of x over g prime of x. So let's calculate two limits. Here, the limit of cosine of x over pi subtract 2 pi as x approaches pi. If you plugged in pi over 2, you'd notice that you'd get 0 over 0. And you know that this is an indeterminate form. Therefore, you can apply Hospital's rule. Hospital's rule states that that limit as x approaches pi over 2 is the same thing as differentiating the numerator and the denominator. That would be negative sine over x over negative 2. And now if you plugged in pi over 2, you'd get negative sine pi over 2 over negative 2. And from the start of the seminar, I gave you a chart and where it said the sine of pi over 2 is equal to 1. So it would be negative 1 over 2, so 1 over 2. Is it pi in
pi negative 2pi supposed to be an x. Is that supposed to be an x there?
Yeah, it is supposed to be an x.
No. Pi minus 2pi. It should be 2x.
Oh, yeah, sorry. Yes, that is 2x. Else the derivative of that would be 0. Yes, thank you. Okay, for the second one, it looks pretty tricky. But if you get something like this, you always want to simplify it. So if you simplify the given, you multiply 1 over x by e to the x minus 1 and 1 over e to the x minus 1 by x, which you'd get e x minus 1 subtract x over x times e to the x minus 1. I know I'm skipping a lot of steps, but this is just pure computation. So this is equivalent to,
Can you scroll slow? I didn't get it.
oh, okay, yeah, sure, sorry. I hope that's better. Now you'd notice that here, if you tried plugging in 0, you'd get an there. If you plugged in 0 there, you'd get an indeterminate form. So you could apply Hospitals once again. So if you apply Hospitals here, you would get e to the x minus 1 over, there's product rule, so differentiate the first.
Isn't that the rule?
You differentiate the first term, 1, you keep the second term, e to the x minus 1. There's addition. Now you keep the first term and you differentiate the second term, which is just e to the x. Why would we even need to simplify? If we plugged in 0 in the first step, we would get.
So when we say that those indeterminate forms, we mean those can be simplified to 0 over 0 or infinity over infinity. Only from there you can apply L'Hopital's rule. If it's infinity over infinity or 0 over 0. If it's infinity minus infinity, that just means it can be simplified to something that's infinity over infinity or 0 over 0. But you need to get an expression of that form.
Now, now you could simplify this even further. So limit of x approaches 0 would be, you could, since you applied L'Hopital's rule here, it doesn't say you cannot apply it once again, because this again would be an indeterminate form. So once you apply it again, differentiate the top would give you e to the x. Now if you differentiate the bottom, you get e to the x plus e to the x plus e to the x. Oh, x to the e to the x. Oh. You get x e to the x. Where here you're applying product rule once again. And now you can simplify, you can plug in the 0. So you get e to the 0 over e to the 0 plus e to the 0 plus 0 times e to the 0. E to the 0 or any number to the power of 0 equals 1. 1 over 1 plus 1 plus 0, which gives you 1 over 2. Now, indeterminate powers, I believe Natalia went over this. If not, we had a question like this on our exam, and I feel like this is a very good topic that you should also learn. So, in case the limit is of the form limit of x approaches a, f of x, or g of x, and produces a form 0 over 0, infinity to the power of 0, 1 infinity to the power of 0, then we can use the following. So limit of x approaches a of f of x to the power of g of x, that is equivalent of x to the a e to the ln of f of x g of x. And these are the basic properties of ln. This is equivalent x to the a. This is equivalent of g of x ln f of x, since you're able to move the power down. Now, since you know that e to the x, and there should be an e. Yeah, yeah. Now, since ex is continuous everywhere, you can write this as e to the limit of x approaches a of g of x ln of f of x. Now, since we also learned Hospital's rule, we can change this into a rational. So this would be e to the limit of x to the a ln of f of x 1 over g to the x. The main reason why you're doing this is so that you could apply Hospital's rule in the future of a limit that you do not know how to solve. So for an example, we will be using the indeterminate powers rule. So here, as you can see, if you plugged in x to infinity, you will get the form of infinity. You get an indeterminate form because you have a number to a power of infinity. So in order to solve this, you would substitute this instead. So let f of x equal 1 plus a to the x, and let g of x equal x. So since we're just plugging in the value, we can write that as e to the limit of x approaches infinity be ln of 1 plus a to the x all over 1 over x. Now, that's equivalent. And now you could apply Hospital's rule. So you'd get e to the limit of x approaches infinity. So when you're differentiating a ln function, you get 1 over whatever's inside ln, so 1 plus a to the x. And you differentiate whatever's inside. Since 1 plus a to the x is inside, you would apply quotient rule, and we're just skipping the steps. You get 1 minus a over x squared, where a is real number. Should be, there we go. And then you would have to also differentiate the bottom. Bottom is another quotient rule, so you would negative 1 over x squared. And then if you subbed in x equals infinity into there, you would get that it would be limit of x to the infinity of 1 over 1 plus a to the x negative a over x squared over negative 1 over x squared would give you a. Therefore, do not forget the e. Therefore, your final answer would be e to the a. Also note that, I did miss a step, so you could also simplify it. So I did not show the simplifying, so you could cross this out. and that out to just get 1 over 1 plus a to the x a. Now, if you subbed in infinity here, you get 1 over 1 times a, which is equivalent just to a. Yeah, sorry, I should have explained fully. Now, for the second question, you would think that this question is you wouldn't know how to solve this question. So instead of if you plugged in infinity, you would get that this would be an indeterminate form. But you can also manipulate the given information into an indeterminate form where then you can apply Hospital's rule. Also notice that you know the derivative of arctan x. So you could write that limit as x approaches infinity as 1 over x over arctan of x. There should be a negative sign there, sorry. Now you can, if you plug in infinity, you get 0 over infinity, which is an indeterminate form.
Yeah.
Therefore, you can differentiate the top and the bottom. So you get x to infinity, you get 1 over x squared negative. And the derivative for arctan x, if you look at the equation sheet at this very start of the seminar, it is, this should be 1 over 1 plus x squared but notice that there is a negative sign here, therefore you have to include the negative sign. Now, if you simplify this, you get limit of infinity of negative 1 over x squared multiplied by 1 plus x squared over negative 1, which would give you limit of x to the infinity of, that crosses out 1 over x squared plus, yeah, 1 over x squared plus x squared over x squared. Now you can sub in x equals infinity, which you get 1 over infinity, which is 0, plus just 1, which is equal to just 1. Now, the very last example we have is using squeeze theorem. So every time, if you have a trig function, if you have a trig function that you do.
Okay, one sec. Okay, I think he meant infinity over here. It's actually infinity over infinity because 1 over infinity, if you plug in x equals infinity here, it's actually equal to 0. So I think he meant infinity over infinity.
Arctan.
We'll come back to that question.
Okay. Yeah, I think we're just running short. We have a lot more questions, so we'll come back to that at the very end. For this question, if you ever encounter a trig function and that you do not know how to solve the limits, you'd try to use the squeeze theorem. So here you know that cos of n times x is always going to be between 1, negative 1, and 1. You also know that sine of a number is always going to be negative 1 to 1. And you know that multiplying them will also result, or multiplying or applying an exponent of them will also result in a number that is between negative 1 and 1. Therefore, you can say that negative 1 is in between cos of x sine squared and negative 1. Does everyone understand this? Okay, so now we have this equality, we want to get a form like this. So here you would multiply everything by 1 over n to the power of 1 over e. So if you multiply by 1 over n to the power of 1 over e, so you get negative 1 over n to the 1 over e. Note that 1 over n to the 1 over e, it will be always positive. So 1 over e is always positive, and since n is a part of the natural number plus, it is also be positive. So the inequality, the signs do not flip. So since you're multiplying everything by 1 over n to the power of 1 over e, you would get n sine squared n less than or equal to 1 over n to the power of 1 over e. And by squeeze theorem, you could evaluate the limits on the left-hand side and the right-hand side, and if they equal, therefore you know that the limit of the equation in the middle is the same. So if we calculate the limit of x infinity, so this line, okay, so you know that cos of x is always between -1 and 1. So if cos of anything is between -1 and 1, and you know that sine of anything is between -1 and 1. Sine of any angle is between -1 and 1. So if you multiply the two terms, you get a number that is also between -1 and 1. Therefore, we can come up with this equality.
Does that make sense?
I'm getting no response, so I think I'll just move on. So here, if you evaluate -1 over n to the 1 over e, and you plugged in infinity, you would get -1 over n to the 1 over infinity, which is equal to -1 over n to the 0, which is equal to -1. Similarly, if you calculate x to the infinity over -1, +1 over n to the 1 over e, you get +1 over n to the 0 equals, is it 1? Oh, yeah. Oh, this should be, did I mess up here? I 1 over -1 infinity. I think I did mess it. I think the question's wrong. Why are we substituting x into? Yeah, the limit should be 0. -1 e 1 over e. The limit should.
Okay, we'll move on to differentiation for now. We'll come back to this in a little bit.
I'll do it on the side.
He's just gonna review, yeah. Okay, so let's move on to differentiation. If I'm moving too fast, just let me know, and I'll go at slower pace. Okay, first we have a simple example of simple product law.
Oh, sorry. Yeah, I did make a mistake. We're subbing in n. Yeah, we're subbing in n. There should be a pi. Oh my god. So, okay. So instead of cos n to the x, there should be n. Sorry. I think we made a mistake when we're copying down the questions onto the sheet. So let me just go through go through this and change it. So this should be n times pi. There we go. All that makes sense. This should be n times pi over n. Now we're evaluating the limit as n approaches infinity. N approaches, not x approaches infinity. N approaches infinity. Infinity. Erase all this. So this should be -1 over infinity equals 0. 1 over infinity equals 0. Therefore implies that limit of n to the infinity of cos n to the pi or sine squared to the pi over n 1 over e equals 0. Yes, thank you.
Okay, let's go back to my part. Okay, so differentiation. So this is basic product law. We'll start off with an easy example. You differentiate let's write f prime x actually. Okay, so f prime x is equal to, differentiate e to the power of 3x, which is 3 times e to the 3x. Then we write the second term. In case you want a refresher, yeah. So that, and then plus we write the second term, write the first term, and now we derive the second term. Remember, the derivative of ln, like my partner said, is 1 over that value, x squared plus 1, times the derivative of that value, times 2x. Now, you can simplify this further, and you get 3e to the 3x ln x squared plus 1 plus 2x e to the 3x x squared plus 1. So that's your simple product law. Now question 2. Okay, when you first see a question like this, you should recognize that this is way too hard to compute normally. So this is a good indicator that you need to use logarithmic differentiation. The way this works is you would take ln on both sides. So ln f of x equals ln x minus 1 to the power of 12, 2x plus 1 to the power of 5, x squared minus 2 to the power of 100. Now, remember our ln properties that in case you didn't know, ln a plus b, a times b, my bad. Ln ab equals ln a plus ln b. Ln a over b equals ln a minus ln b. So let's apply that idea here. That's the main point of logarithmic differentiation, is to do that. So now we can simplify this left side to ln x minus 1 to the power of 12 plus ln 2x plus 1. If I'm going too fast, just let me know. Minus ln x squared minus 2 to the power of 100. Now we know our ln properties. You can bring 12 down. You get 12 ln x minus 1 plus ln 5 ln 2x plus 1 minus 100 ln x squared minus 2. This, we just brought the terms down. Okay. Now, okay, so we have ln f of x. Now let's differentiate both sides. We can do that, right? Take the derivative on both sides. So take the derivative of both sides. What's the derivative of ln f of x? You get 1 over f of x times f prime x is equal to the derivative of this. So that's 12. Remember ln, it would be, keep in mind, make sure these should be absolute values. This is actually important. Let me highlight this. These should be absolute values. You need them to be absolute values. They should always be absolute values. Let me just highlight that. Yeah. Go fix that. Okay. So you get 12 times 1 over x minus 1 times the derivative of x minus 1, which is 1, plus 5 times derivative of 2x plus 1 times derivative of 2x, which is 2. Okay. Ln 2 or x plus 1, yeah. 2 minus 100 times the derivative of that, which is x squared minus 2, times the derivative of x squared, which is 2x. We can clean this up a bit. So you would get f prime x over f of x equals 12 over x minus 1. 12 over x minus 1 plus 10 over 2x plus 1 minus 200x over x squared minus 2. So you have that. The good thing here is you can simply move your f of x to the other side. So you get 12x minus 1 plus, plus 10, 2x plus 1, 200x, x squared minus 2, where we can just plug our original f of x back in. I'm not going to write that because it's going to get messy, but you can just plug your f of x back in, and that will be your final answer. That's the good thing about logarithmic. You can leave it in that form, and it is equivalent to doing the derivative naturally. Now, this is a really quick example I just wanted to go over. Is if you take f prime x, now the derivative of a piecewise, you just take the derivative of each element. So it seems pretty easy, 2x, 0, negative 1. But notice these inequalities that are over here, these ones. Notice that you have to check if they still hold. So we got x less than equal to 0. Now we want to see is 0 less than equal to x. You can check at x equals 0, 2x is equal to 0. That's true. So since these are equal at x equals 0, the equality does hold. X 0 less than equal to x. Now we need to check the other side though. At x equals 3, 0 does not equal negative 1. So the second part is not true. So we cannot write that. So it will be less than 3, and then this will be x greater than 3. And it's undefined at x equals 3. So that's just a good thing I thought you guys should notice. Now, this is a hyperbolic function. The derivative, again, it just goes by the definition, quotient law, but the important thing to know is that to know the domain. This came up on one of my quizzes last year, and I think we had a domain question similar to this on the final exam. So if you have something like this, you know by your hyperbolic differentiation. If we apply quotient law, you get 1 over the square root of 1 minus x squared times sine h of x minus cos h of x, right? Because the derivative of sine hx is cos hx times sine inverse x all over sine hx squared. Now, the important thing to note is the domain. Okay, sine h of x, its domain goes from negative infinity to infinity. However, you should remember the domains of all your inverse functions. If you don't remember, your inverse of sine, it looks something similar to this. Let me just draw a quick diagram where this is negative 1, this is 1. Oops, kind of hard to draw a straight line. Yeah. So your domain only goes from negative 1 to 1. So you have to specify here that sine inverse x, the domain of this function actually, is only defined on negative 1 to 1. So it's important you guys remember that. Now, here's a last different type of differentiation. This one, you should know right away that since you see both x terms and y terms, that you need to use implicit differentiation. So let's apply that here. So you would first take your sine, take derivative on both sides. So you will get cos xy, but you need to multiply by the derivative of the inside. So xy. So times the derivative of xy, you apply product law. You get y plus x times dy by dx. Whenever you're deriving y in implicit differential, wouldn't 0 be included in the domain though? Would 0 not be included in the domain? Sine h of x. Oh yeah, sorry. Yeah, I have that in my note. I missed that part. 0, because it's not defined at 0. Sine h of x is 0 at 0, and then you get 1 over 0. Now, back to this one. So you get times y plus x. So whenever you're deriving y, you have to write dy by dx. Make sure to remember that. So you get this is equal to 2x plus, plus 3y, yeah, plus 3y squared dy by dx. Now we need to solve for dy by dx because that's the derivative. That's what we're trying to solve for. So we can factor the cos xy in. So you get y cos xy plus x cos xy dy by dx equals 2x plus 3y squared dy by dx. Let's bring the like terms together. So you have x cos xy dy by dx minus 3y squared dy by dx is equal to 2x minus y cos xy, right? So now we factor out the dy by dx, which gives you x cos xy minus 3y squared equals 2x minus y cos xy. So now we move it to the other side. So dy by dx is equal to 2x minus y cos xy all over x cos xy minus 3y squared. And that will be your final answer. So I'll just put that in green just so you guys remember. Again, if I'm going too fast, just let me know and I'll slow down. Okay. The next portion, optimization.
Does anyone need the question still to write? Or could we move on?
Question 2.
Question 2? Oh, question 2. What about question 2?
I think I think you're referring to this question too.
Oh, you just wanted to see it. Okay.
No problem.
Okay, so while he's copying that down, we will be starting optimization. On your exam, expect at least one question to be an optimization problem. This question will be very similar to the lecture notes that you got. So I believe that you got a cylinder example, and you also got a revenue profit example. So it's going to be one of them. For our final, I believe we got profit and revenue.
Yeah.
Profit, which is our second example. So in this example, a soup manufacturer is considering using a new large cylindrical can of soup for commercial sale of volume 2000 pi centimeters cubed. In order to minimize cost of material, they commission you to find the dimension of the can with the least surface area. What can you tell them? So with these type of questions, you want to really write out what you know and what you want to know. So let's start off with what do we know? Or before any of this, you can always draw a diagram. So this is a cylinder. where this would be your height. Height, and this would be your radius. So what do we know? So the volume is equal to the base times height. And here they gave us that the volume is 2000 pi centimeters cubed. The base is a circle. The area of a circle is pi r squared. And you know the height is just h. Now, what do you want to know? You want to know the surface area, that you want to minimize the cost of the material. So you want to find a dimension where your surface area is at its minimum. So area on the side is equal to 2 pi r squared. This is because you have two circles and surface area. And you would have 2 pi r height. And this would be your height of your cylinder. So if you, going back, if you isolate h, you get h equals 2000 pi divided by pi r squared, which is the same thing as 2000 pi, 2000 divided by r squared. Now, since you have the height, you can plug it into your surface area, the surface area equation. So that would mean you get 2 pi r squared plus 2 pi r. The height would be 2000 over r squared. You can simplify this to 2 pi r squared plus 4,000 pi r. That cancels out and you multiply it by 2. And notice that your radius is always greater than or equal to 0. Now you want to find the dimension that minimizes the surface area. And what does this mean? This is essentially telling you that you want to find the minimum point in your surface area equation. And how do you do that? So you essentially want to find the critical points. So if, let's say your surface area, your equation was defined by A, so that is equal A. You want to find A prime and set it equal to 0. And this would mean that you get your critical points. So let's do that. So first, let's find A prime. A prime is differentiating your equation. So you get 4 pi r, subtract 4,000 pi r squared. Notice that when you're differentiating the second term, it's you're using the quotient rule. Now you'd set A prime equals 0. So 0 equals 4 pi r subtract 4,000 divided by r squared. Now, if you simplify that, you get 4,000 pi over. But if you move one term to the other side and you isolate for the radius, you get 4,000 pi r squared equals 4 pi r. Now you can multiply r squared to the other side, and you could divide 4 pi. So 4,000 pi divided by 4 pi are 3. And this would give r equals 10. But the thing is, you want to check if r is in your domain. You want to check it, and r is the minimum point. Yes, one sec. Put this in. Okay, I think we're good there. Okay, so you want to show that R at 10 is your minimum point. Oh, sorry. Okay. Yeah, so let us check if at R equals 10, your at your minimum. There's two ways to check. You can differentiate A prime once more, or which is, I would say, it would be one of the easier ways, but I'll just do another way, which is more, so you get a better understanding. So you know A prime is equal to 4 pi R3 subtract 1,000. I'm just simplifying our original equation. So I'm multiplying the first term by R squared and getting a common denominator. Now, if by plugging in values to R, you will notice that A prime of X is less than 0 if R is between 0 and 10. And if you plug in values of R that is greater than 10, so A prime of X is greater than 0 if R is in between 10 to infinity. So what does this tell you? This tells you that your minimum R at R equals 10 is in fact your minimum point. Therefore, R equals 10 is your minimum point. Therefore, radius equals 10. Then at the very top, do not forget about your height. You plug in R equals 10, so you get H equals 2,000 pi over 10 squared, which gives you 20. So your dimensions are radius equals 10 and height equals 20. Oh, 20 pi, yes, 20 pi. 20 pi. Okay. Now we have another optimization problem. This is a revenue, demand and revenue question. The managers of a 100-unit apartment complex knows from experience that units are occupied if rent is $800 per month. A market survey suggests that on average, one additional unit will remain vacant for each $10 increase in rent. What rent should managers charge to maximize the revenue? So your first step is to determine a demand function. So determine a demand function. Now, in the question, they gave you a couple of hints. You know that the demand function has a point of 100 and 800. Since that 100 unit, if you have 100 unit apartments that are rented, you know that each unit will give you $800, or it is $800 per month. You also know that every $10 increase, there is one less apartment rented. So if we look at your one equation that you all should know, y equals mx plus b, you know that I forgot, this implies that the slope equals -10. So y equals mx plus b, you know that you have 1 point, 100 and 800, so sub that in. And you also know that slope is -10. 100 plus b. And if you isolate for b, you'll get 1800. Therefore, your demand function is in fact x plus 1800. So this would be your demand function. 2, 3, you want to calculate your revenue. Your revenue is basically the price charged multiplied the number of units rented. You want which is equal to price charged multiplied by units rented. So this is Rx is equal to X is the number of units that were rented, and you know the price that is charged is that. So you would sub negative 10x plus 1800, which will give you plus 18x, which is in fact revenue. Now you want to maximize the revenue, and how do you do that? You want to differentiate R of X, so max R of X, and so you differentiate R of X, which would give you negative 20 of X plus 1800, a very simple differentiation. Now, in order to get your critical points, you let R of X equals 0 to get your critical point. So 0 equals negative 20x plus 1800. You isolate for x, and you would get 20x equals 1800. X would indeed be 90. Now, you got one of your critical points, but you do not know whether your critical point is in fact a maximum. So you would have to check if x equals 90 is a maximum point. And in order to do that, since I did not do this way in the first optimization problem, I will calculate r prime of x, or calculate the second derivative of r. And you can see that this will always be negative 20 of x plus 1800. Derivative will always be negative 20. So this means that the second derivative is always negative. So that means that the critical point that we found is in fact your maximum critical point. Therefore, in order to maximize the revenue, you would need 90 units rented, and the profit that you get is P to the 90, which is equal to negative 10, 90, or this should be y to the 90. So if you sub in y equals 90, let us say this P to the x. So P to the 90 is negative plus 1800, which if you simplify is $900 per month, which would give you a maximum revenue. Could I see? Okay. Yeah, okay.
All right, now we'll move on to a graphing question. So I looked at your week 12 notes that you guys got this year, and a lot of them were rational functions. So I thought a good example would be to give you guys an example of a non-rational. This is actually be very, very similar to the graphing question we got. So there's a few tricky parts. Okay, so first of all, let's calculate the domain. So if you look at let's look at the graph of each function on its own first. So x to the 4, as you know, is just a bigger parabola. Its domain goes from negative infinity to infinity. E to the power of x, on the other hand, it goes from, it has a horizontal asymptote, and it goes here. Its domain is also negative infinity to infinity. So the domain of them together also negative infinity to infinity. I think that's pretty simple. Symmetry. So now, okay, so first let's calculate, we know f of x, let's calculate f of negative x, which is equal to negative x to the power of 4 e to the negative x, which is x to the 4 e to the x. The reason I put positive here is because it's to the power of 4. So no matter what value, whether it's x or negative x, to the power of 4 is going to be equal to x to the 4. Because to the fourth power is like putting it to the second power. It's always going to be positive. So we have that for f negative x and negative f of x. We get negative x to the 4 e to the x. So you can clearly see f of x is not equal to f of negative x. And f of x is not equal to negative f of x. So therefore, no symmetry.
Oh, not equals.
Oh yeah, not equal. No symmetry. Yep. Now x-intercepts. So looking when x to the power e to the x equals 0 is the same as looking as when they individually equal 0. So x to the power of 4 equals 0. You get x equals 0. Fourth root of 0. Yeah. E to the power of x equals 0. However, you take the ln equals ln of 0. X equals ln of 0. However, notice that this is undefined. So it is not one of your zeros. Your only zero is x equals 0. Now let's look at asymptotes. So when you first look at this function, you think x to the power of 4, e to the power of x. There's no asymptote. Like the way you guys learned in lecture and commonly know is like look at, if you have a rational, look at the coefficient. But even though this is not a rational function, there is still an asymptote, because remember, this is our graph of e. It has a horizontal asymptote at x equals 0. But now, so we have x to the power of 4 e to the x. So this has an asymptote at x equals 0. Now, if you think about this logically, x to the power of 4, we said before, is always greater than 0 for all x. For any value of x, if you take a negative number, a positive number, it's going to be positive. So a positive number times e to the power of x, which is always above the horizontal axis, if you think about it logically, it's going to remain above the horizontal axis, right? The horizontal asymptote will remain. Oh, and by the way, it can cross the horizontal asymptote. Like we have x equals 0 is x-intercept. That is possible. As an asymptote is just defined by the value that it approaches. So like over here. Okay. So you can clearly see that there's an asymptote at x equals 0. This was a step that a lot of people in our exam missed because it's something you wouldn't trivially see. So now let's calculate the derivative. Okay, so f of x equals x to the 4 e to the x. Let's calculate f prime x equals 4x cubed. We derive the first term, we write the second term, derive the second term, which is still e to the x, because like it's actually e to the x. The derivative is e to the x ln e, which is just 1. So yeah, e to the x, x to the power of 4 x cubed, yeah, plus e to x to the 4. Now let's calculate the critical point. So the critical points, if you remember, do we show that? Yeah, asymptote. It doesn't really cross it. It has an x-intercept at it, but yeah, in the graph you would show it. Yeah, the x-intercept. Critical points. So we set the function, the f prime x to 0, 4x cubed e to the x plus e to the x, x to the 4. A good way to do this is you can first factor out e to the x, x cubed. Then you're left with 4 plus x on the inside. And just like we did for the x-intercepts, calculate them individually. So you get e to the x, which we showed was undefined when e to the x equals 0. X cubed equals 0 implies x equals 0. So that's one of our critical points. And 4 plus x equals 0 implies x equals minus 4. So that's another critical point. So we have two critical points, 0 and minus 4. And it's important you do write this. I remember seeing this in Natalia's notes as well. 0, -4 is an element of the domain of f of x. This is important, even though it's quite obvious since it's negative infinity to infinity. Make sure you write this. I do remember marks being cut off for that. Okay, let's move on to the second derivative. So we have f prime x equals, let's go back to the original way we wrote it, just so it's easier to derive. Plus e to the x, x to the 4. If we calculate f prime x, we have to do product law twice. So you get 12x squared e to the x plus 4x cubed e to the x plus 4x cubed e to the x plus e to the x, x to the 4. Similar to before, you can factor out x squared ex. You get 12 plus 4x plus 4x plus x squared. Let's just rewrite that a little more cleanly. X, so you know that's a polynomial, 8x plus 12. Yeah, okay. Let's move on to the POIs. Okay, POIs is when the second derivative is equal to 0. So 0 equals x squared e to the x, x squared plus 8x plus 12. So now you get so like this is the general format you should follow for the exam as well. I'm pretty sure she breaks it up like this as well. Like this is how she did on the worksheet as well. So I followed this a similar format. And yeah, try and show all your steps. So now we can take the same thing as we did the last two times. Let's take each one is 0. The reason we can do this, by the way, is because when one of these terms is 0, the whole product is 0, right? So you get x equals 0. That's one of them. Undefined. So we can factor this and you get x plus 2, x plus 6 equals 0. So we have x equals -2 minus 6. Okay. Now Natalia likes to draw a chart. I saw the way she did it. Even in first year, I never really fully understood it. So I'm gonna do it a way that we learned in high school, which I think is a lot better. So you know, so you, first of all, you write down your critical points, POIs, and vertical asymptotes, and then you make a chart where each one you write is less than it, equal, and then like each interval between each one of the values. Just make a chart of it. So you know, and then we'll look at the sign. So we're looking at the signs here, not the value. So if you take any value of x less than -6 and you put into f prime x, you get a positive term. And you know, critical points only change. You don't have to compute each one of these because you do know that critical points only change when they're 0. So we calculate our critical points to be 0 and -4. So we know this is positive, this is positive, this is positive. Here we have a 0 critical point. And then it switches signs after the critical point. If you want, you could, like, to double check your work, plug in each value, but yeah. So do the same thing for f prime x. Are we gonna get it? What we did on our exam, yeah, we got it broken up into this format, but you guys have different material being covered. You guys did related relations, so it could, and it's an online exam. I think you should be ready for both of them, but we did have it broken up like this. Yeah, so we get a 0 here because that's a POI. So same concept as the critical point. It switches signs at the thing. 0 plus, 0 plus. This one at the end actually 0 is all three. It's a POI, a critical point, and a x-intercept. And if you actually plug in a value into f prime x, you'll see that it's positive on both ends. So actually, it's probably better you do like plug in a value and double check your work. I'm assuming you guys have calculators allowed. Now, a way to get f prime x, f of x, that'll show the shape, is look at this term first. So if
no calculators.
No cal. Oh wow. Okay, then it's probably better to follow this. But just if you have a 0, it was a unique value because it was a POI, it was a critical point, and it was also an x-intercept. So like that one was like most of the time, like you'll rarely ever have this case unless it's a vertical asymptote. Okay, so it's a horizontal asymptote. Yeah, but what's it called? Yeah. So you look at the plus over. Oh, whoops, I erased it wrong. You look at the plus here, and one way to know is if your f prime x is you have a smiley face and a sad face. Okay, so just stay with me. So if this is a plus, you're looking at the smiley face. And then if the top one is also a plus, you're looking at the increasing side. So then you can put increasing. It helps you see the shape of it. So then this is a POI. You should write the point here, -6, whatever the point is. Yeah. Now this one, on the other hand, is a negative. So you're looking at this one over here. And the top part, this part is a positive. So since it's a positive, you're looking at the positive side, this part. Whenever the top one is positive, you're looking at the increasing portion. And the bottom one tells you whether it's a smiley face or a sad face. Okay, so now you get here. This is a local max. If you want, you guys could do it in Natalia's way. I didn't understand it very well. So now minus, so minus means you look at the sad face, and the top is -2, right? So now you're going to be looking at the decreasing. You're looking at a decreasing side of it. So you get decreasing. Then you have another POI here. If you follow this format, you should get, so that would be like that. This would be like that. This is a local max. And then this one would be like that. Okay. Let's show the graph of it now. Okay, so recall we have an x-intercept at 0, 0. -4, we have a max. So, ooh, I'm not very good at drawing. -6. Okay, so let's sketch our graph. Be like, it will go up that way. It would cross the x-intercept. It will come around to like that, and then it'll go across like that. Okay, I think that's pretty well. Okay, so this is a POI. If you can, write the point as well, but I don't think it matters unless they specify it. This is your maximum. And you should mention that, you should show that you have an asymptote here. X equals 0. Asymptote. So that's generally how the shape of your graph should look. Was there anything, do you guys understand the smiley face idea? Or like, okay, let's move on to antiderivatives.
Just wondering, did you guys learn antiderivatives?
Yeah, we did.
Okay, you did.
Okay.
Okay. Okay, let's do the related rates, then come back to the antiderivatives.
Okay, yeah,
I
we'll do
don't
the
think
related.
it's that important.
So since this was never covered in ours, I tried Googling it and learning it myself yesterday night. So again, bear with me, it might be a little different than how you guys learned it. But yeah. We'll also show you a very helpful link after this. Like I found 2 questions that were very similar to the ones you guys got on your week 12 worksheet. So I'll send you a link to that. We're doing one of the assignment questions from that, one of the questions that doesn't have a solution. You'll see all the questions that do have a solution to you. So, okay, let's draw a diagram first. So a hot air balloon is attached to a spool of rope that is 125 feet away from the balloon when it is on the ground. The hot air balloon rises straight up in such a way that the length of rope increases at a rate of 15 feet per second. How fast is a hot air balloon rising 20 seconds after it lifts off? Okay, so first of all, let's draw a graph, a picture just to help better represent it. So you have a spool. This is your balloon. And so now let's label values here, H, R, L. What's the difference between antiderivative and integration? They're basically the same thing. They're pretty similar.
Oh yeah, they're the same thing.
Yeah. You'll go more in depth in that with A37.
I believe Natalia used antiderivatives instead of integrals so that you do not get scared.
But they're basically the same idea for now. So is the length. R is the... I'm trying to follow the format again of how she did it, where you first write your given. So H is height, H is the height of the balloon. So now let's write down the numerical information we have. The numerical information we have is, so L equals 125 feet. We were given that. We were also given the change in which the road distance increases is 15 feet per second. Okay, so 15 feet per second. So now one thing you can notice here is that it says that the rope is 125 feet away when it's on the ground. It rises in such a way that the length of rope increases at a rate of 15 feet per second. So you know that from this, you can create a function that is R equals 125, the starting distance, plus for every second, plus 15t, where t is your time. Okay, so now by Pythagorean theorem, which you can see over there, you have r squared equals L squared plus H squared. L squared, L is 125, so 125 squared plus H squared. Okay, there's no, okay, good. Okay, so now what do we want to find? We want dH by dt, because we want the height, we want to know how fast, so at that specific height, how fast is the balloon rising? 20 seconds. What? Why does it keep switching to this? When time is 20 seconds. Okay. Let's go to, oh, that was step 4. I missed something. 3. Okay, 5. So r squared equals 125 squared plus h squared. So first let's solve for h at t equals 20. So since r is the distance, we have our formula, r equals 125 plus 15t. So plug in 20 here, you get equals 125 plus 15 times 20, which gives you 425. So you get 425 here. So we're using this value when time is 20. So from here, you can see that you get 425 squared because r equals 425. Okay, so you get 425 squared equals that. 125 squared, yeah, you leave that 125 squared plus, then you solve for h. I already did this on my sheet, so I'm just gonna write the value. So you should get h equals 406.20. If you guys want to verify that, you get that as your expression. Okay, now we got in terms of that. Okay, so now go back to our original equation. R squared equals 125 squared plus h squared. Now we use implicit differentiation. You get on both sides, so 2r times dr by dt. Take it with respect to t. You get 0 because this is a constant, plus 2h dh dt. We have all the values we need. We can now solve for dh over dt. Oops. So, oh yeah, and recall from above, we have dr over dt we were given right here is 15 seconds. So we know the value of that. And so yeah, okay, so we have, so first of all, we can cross off the twos. So you get r times dr dt equals h dh dt. We want to solve for h. So we know our r, which we calculated at t equals 20 seconds. I'll just write it again. R equals 425 from here. So you get 425. Remember, dr by dt is 15 by a given. Equals h times dh by dt. We know h as well, which we calculated over here, which evaluates to 406.25, 406.20. So you get dh over dt equals 425 times 15 divided by 406.20, which is approximately 15.69 feet. I verified this online, but the question I got this from didn't have a solution key, but I checked multiple sources online and it matched my answer. So that would be your final answer. We can show you the link. Let me get the link of the.
Okay.
Go on.
While he's doing that, I will go over the basic integrals. So who here likes integrals or antiderivatives? Or does everyone think they're hard?
They're not bad.
Oh, whoever's, could you say that again?
I said they're not bad, but I'll probably have to review them. The last time I did it was like grade 11. So
Okay. I'd say after 8:30, 8:37, you'll like integrals very much. Kathleen is a great teacher. So for the first question, we will use U substitution. I believe U substitution and by inspection are the only two methods that you've learned. So if one doesn't work, like by looking at this integral, coming up with its antiderivative isn't too bad, but I'd rather use U sub. So here you would say that let U equal x squared. Now you could differentiate the left-hand side and the right-hand side. So let du equal 2x dx, or this should be dx. Yeah, always make sure you include dx. You'll lose a mark, and that's a very dumb way to lose marks. So here you could see that you could there's a way to get x dx by whatever we have. So let's isolate for x dx. So we can divide both sides by 2. So that would mean you get x dx. So since we got something here, so x dx equals du over 2, you can take this, you can replace it by du over 2, and you can take this and replace that by u. So this would be equivalent to the integral of e to the u du over 2. And you know that constants, you can take out constants. This would be 1 over 2 integral of e u du. Since you're differentiating in terms of u, since you're integrating with u, integration of e to the u is always e to the u. So it would be 1 over 2 e to the u. Now, am I missing something here?
Yeah, the recording will be posted.
Would this be my final answer?
don't you need plus C?
Yeah. So you do not want to forget this. I've lost too many marks by forgetting this. Also, you do not want to forget not subbing back u. So this would be 1 over 2 e to the x squared plus c, and this would be your final answer. For this question, this question is very simple. Integration can split over addition. So this would be equivalent of integration of x to the 5 plus integration of x to the 4 over 3 plus the integration of x to the negative 2. And there's dx, like you shouldn't forget these. Now, integration of x to the a is basically x to the a plus 1 over a plus 1. So you want to remember this. Like this is something that you should know. So if I integrate each one, I get x to the 6 over 6 plus x to the 7 over 3 times 3 over 7 plus x to the 1. Yeah, it's because you're adding 1 plus 1 plus c. And this would be your final answer. Also, okay, so I think we're done, but going back to the question that I messed up pretty bad. Where is it? Okay, this question. So the whole question, I will redo it. Yeah, oh, -1.
Yeah.
Yeah, basically. It is like, oh, where is it? Did I mess up? Oh yeah, -1. Yeah, forgot that. Whoops. Okay, going back to this question. Eraser. Okay, so the question itself is wrong. I thought that it should be limit of x to the infinity 1 over x times pi over 2 subtract arctan of x. So if you sub in infinity here, you'd get 1 over infinity multiplied by pi over 2 subtract arctan of infinity, which is in fact pi over 2. So what do you have here? You get 1 over infinity times 0, which is one of your indeterminate forms. Do you have an okay? So I would, since we're going over time, I think I'll just leave this like this as a the steps are the same. So you would bring limit of x to the infinity 1 over x, bring it to a form that where you could use L'Hopital's. So pi over 2 subtract arctan of x. Now you differentiate the top and you differentiate the bottom using L'Hopital's. So you get limit x to the infinity.
Wait, I had a question.
1 over x squared. Yeah.
If the initial form is already indeterminate, then why do you need to manipulate it more? Like just the initial.
Because when you're differentiating, you get 0. Like if you do L'Hopital's right away, you get differentiating the top will give you 0.
Mm-hmm. Okay, I see.
It's already a 0 with no. Let's. Or like this could be equivalent to 1 over no. It's already 0 with no. That's wait, so which step is 0? Are you talking about this step or this? Because infinity times 0 is indeterminate. So you cannot, like, the form, this form itself is indeterminate.
I think like what I mentioned earlier is you have to make it infinity over infinity or 0 over 0 before you can apply L'Hopital's, right? So this expression over here is the same thing as writing 1 over pi over 2 minus arctan infinity over infinity. And then you get 1 over 0 equal infinity, and then infinity in the bottom. So you get infinity over infinity, and that's why you can apply law of Patel's rule. So, because you need to always evaluate it into this form or 0 over 0. When he mentioned earlier that any of these forms work, it means they can be simplified into, not 8. They can be simplified into infinity over infinity or 0 over 0. But you have to first simplify before you can apply law of Patel.
But I think if you sub in infinity here, we get this form. So I don't know how that equals pi over 2. Yeah, the inverse 10 of infinity equals pi over 2. Yes. So moving on, you get differentiate the bottom, you got negative 1 plus x squared. Note that there's a negative here. Substitute infinity and arc. Yes.
Yeah, in arctan you get pi over 2, then pi over 2 minus pi over 2 is here.
Okay. I'll move this here to get more room. So limit of x to the infinity, you can simplify this. Negative 1 over x squared multiplied by 1 plus x squared over negative 1. Cross those out. You get limit of x to the infinity, 1 divided by x squared plus x squared over x squared, which is equivalent to 1. Yeah, the original was copied wrong. Yes, thank you.
It's the question.
Oh, yeah, sorry. I should remove that. This is the question, yes. I will fix this before uploading the notes.